Hi, my name is Amy Cheng, and I am a full-stack web developer at New York Magazine, and when I'm not helping the magazine publish stories about sex robots and how glitchy artificial intelligence is a metaphor for our current political climate, I am also an artist, and you'll see some of my art in this talk. So I'm an artist that believes that code is an artistic medium with the same expressive power as traditional artistic mediums like oil paints. And I am interested in machine learning because I feel it could be a sophisticated tool that helps artists break new ground or express old ideas in new ways. And I'm also interested in machine learning because it raises intriguing questions about creativity and art. For example, can a computer be creative and create art we haven't seen before, or can it only propagate the aesthetics and tastes of its training data? So in this talk, I use the act of making art as an analogy for machine learning, specifically the task of style transfer, and I will be using JavaScript to illustrate some of the concepts we'll be coming across. You'll also notice in this talk that there will be barely any math, and it's because the JavaScript libraries that I'll be using in this talk kind of tuck away the complexity. And so these libraries are essentially black boxes, which could be a good or bad thing. Good for beginners because beginners don't need a lot of previous knowledge to get started, but kind of bad once you sort of come across bugs or want to do something a little bit beyond the tutorials. And then if you're trying to kind of move past the beginner stage, you're going to have to do some excavation of the source code. So what is style transfer? So in 2015, a paper titled A Neural Algorithm of Artistic Style was published. And in that paper, the authors described using a neural network that was originally trained to do image classification. And they used this neural network to remake one image in the style of another image. So the first image would usually be a famous painting, like Van Gogh's Starry Night. And then they would transfer the style, that is, remake the secondary image with the features of the first image. Now, internet culture loved this because it seemed like being an artist had finally become democratized. You download this app, you put in your photo, you pick a style, and then suddenly you have created an artwork in the vein of a very famous artist like Picasso or Van Gogh. So why are we using JavaScript? Well, it runs in the browser, so you can share it easily as long as you have a place somewhere on the internet to share your code. Development, when you start with client-side JavaScript, the development environment is kind of easier to set up than with Python. You don't have to worry about Python 2, 3, and if you want to use dependencies, you just link it in your HTML document. Also, JavaScript is kind of a forgiving language if you forget your terminating semicolons, if you mix spaces or tabs, or if you use variables that you haven't defined, it will most likely run in the browser. Also, the community surrounding JavaScript is pretty generous. There are many tools and frameworks for all sorts of tasks being released every day. So in this talk, we'll be looking at two machine learning libraries, Synaptic.js and ML5.js. And here we have code using the Synaptic.js library. We are initializing the architect class, and we're using it to create a feed-forward neural network with perceptrons. Now, a feed-forward neural network kind of takes information, and the information is passed from one layer to the next layer to the next layer. There are some neural networks where there are numerous feedback loops, but we are not looking at those neural networks today. So here we are creating a neural network with perceptron architecture. We have 2 input layers, 15 hidden layers, and 3 output layers. And as we learned yesterday, all that's happening in each layer is a bunch of math. So each time we feel, we think, we cognate, and learn, a bioelectrical signal is being sent through many, many neurons, which is, we have a diagram of a neuron on the right. And the neural network we just created contains perceptrons, which are just basically computational models of the neuron on the right. And if you look at the source code for if you look at the source code for a perceptron object in JavaScript, you'll see activation functions, which we kind of touched upon yesterday. And one way to think of activation functions is basically as a simulation of the rate in which a bioelectrical signal travels through a neuron. So we're going to train our neural network to recreate or paint Ice the dog. And the thing about machines is that they don't see qualities unless you quantify them. So humans would see this picture and say, oh, the dog is white, it's furry, it has blue eyes, it looks pretty happy, it looks like it's fall in the picture. Machines don't see that unless you somehow assign a numerical value to those qualities. So just some housekeeping. This is the HTML page we're using in this demo. We have the image, and then we have a canvas element, which is the HTML node that our neural network will paint on. And then we see the library that we're using and the code and a link to the code that we're writing. So here we are converting our image into numbers that the computer can understand. We are preparing our image for our neural network. The first function gets the image data as an array of pixel values. So so that array or matrix, I have to double check that. That matrix has all the pixel data about the image. And in the second function, which we'll see again in the next block, basically grabs the red, green, and blue values of that pixel at that location. So here is our training function. A couple of things are happening here. First, the neural network is grabbing, so the image that we're looking at is two-dimensional, so our neural network has to grab each pixel row by row, column by column. And then our neural network makes a guess as to what this pixel color should be at that location. And then it is corrected. And this function is being run continuously as long as the HTML page is open. And also after each round of training, after each time this training function is called, the neural network paints the pixel onto that canvas element in a couple of slides ago. So if you take a beginning drawing course, one of the first exercises your instructor gives you is a blind drawing exercise. So you are told to draw something, but you are not allowed to look at the sheet of paper that you're using. And this is because beginners have a habit of not looking at what they're drawing. They'll look at the sheet of paper more often than what they're trying to draw, and this leads to mistakes. So on the right is a blind drawing of the scene depicted in the second drawing. And in order to, so beginners kind of get frustrated at the start of art class because they're like, why doesn't my drawing look like a tree? Why I'm really super frustrated. And it's because they have not really learned to look. In some art classes, particularly life drawing classes where you're drawing humans, you are taught heuristics, sort of tips and tricks on how to measure and how to figure out the proportion of the figure of the person you're drawing. So what's happening here is a diagram found in a figure drawing book written by, I think, Andrew Loomis. And here he divides the face into quadrants. Another reason why art students are kind of taught this heuristic is because there's simply too much information. The human face consists of many features. There's eyes, nose, mouth, but there's also different planes. A person's face isn't flat. There's contours, and there's insets, and there's concaves. And so what using a grid does, it allows the student to kind of focus on each quadrant and also figure out the relationship. Like, how does the eye sit on a face in relationship to the nose, the mouth? How big should the forehead be? When I first started out, I was pretty surprised to kind of learn that the eyes are actually in the middle of the face and not like up top. Because we tend, when we look at a person's face, we're looking here and not really, and we don't really register that their forehead actually takes up most of the sphere of the, well, the almond or whatever face. Sorry. So students develop better habits in terms of looking at what they're drawing, and they also kind of internalize the heuristics they are taught. And in machine learning, we are always trying to figure out ways for our neural network to correct its outputs without much human intervention. Either during training, where in addition to going through the training data, the neural network will double check what it's learned against a validation data set. Or in our demo, we have a backpropagation function that will correct the neural network's guess as to what color this pixel should be. So here are the images our neural network has created at different points of its training. The results are kind of interesting in a modern art kind of way, but they don't really look like ice. And I suspect it's because either we are grabbing the data or we're looking at the data incorrectly, our backpropagation function needs some tweaking, or our neural network is not sophisticated enough. So all our neural network is doing is going through each pixel and looking at color. In the task of style transfer, we are using another kind of feed-forward neural network called a convolutional neural network. And so the top diagram is the feed-forward network we created a couple of slides ago, and the bottom is a diagram of, I think, 2 neural networks described in a paper called Perceptual Losses for Real-Time Style Transfer and Super Resolution. The previous paper I mentioned, you also use a convolutional neural network, but was only trained to detect textures of the style image. Whereas in this neural network, shown here, it was trained to detect multiple features of an image. So the next thing we're going to try to do is repaint or paint ice as a Van Gogh painting. And this is a self-portrait of Van Gogh. We can't use JavaScript to train models. There is simply too much data. I mean, our web browsers take a couple of seconds just to render the CNN website, so can you imagine it going through several gigabytes of images? You'll probably cause the browser to just explode. So for the JavaScript implementation of style transfer, I still needed Python to train our neural network. And so I trained the neural network on the CocoaNet training data, which contains like thousands of images with labels. And so the labels for each image will describe what's in the image. So there's a dog, there's a bowl, there are humans, there's a fire hydrant. And along with this training data, our neural network is continuously looking at the Van Gogh painting to try to figure out what features comprise this painting. And then during the actual transformation of Ice the dog into a Van Gogh painting, our neural network will compare the features of Ice the dog to the features found in the Van Gogh self-portrait and sort of map the Van Gogh features found on the Ice picture, and then kind of sort of transfer those features, or transfer the features in the Van Gogh portrait to similarities found in the photo of Ice the dog. So here is a screenshot of the Python code starting its training, its first round of analyzing the Van Gogh image. Here we have our HTML markup. We have the image of ice. You'll notice that the file name is called ice cropped, and is because the JavaScript library we're using is expecting, can't handle transforming images that are of a different size of the model. So the model, being the Van Gogh portrait, is a square, but the original image of ice was a rectangle. And I needed to crop the image of ice so our JavaScript code would be able to better detect features in both and compare and map features from the Van Gogh painting to the photo of Ice the dog. And basically, here's all the code we need to load the model and to transform Ice the dog into a Van Gogh painting. So just a quick note about ML5.js, which is the library we're using in this demo. So ML5.js is a wrapper for DeepLearn.js, but DeepLearn.js is being deprecated in favor of TensorFlow.js, which is a JavaScript port of the TensorFlow library written in Python. And another thing to know about ML5.js, it is designed to be a more user-friendly wrapper for DeepLearn.js. As such, its documentation is pretty good. It's geared towards beginners. But since it's geared towards beginners, a lot of the complexity is tucked away, as we'll see in a couple of slides. So here is the exact line where we are loading the model. So the model was originally created as a TensorFlow model file, and we needed to convert that into JSON. You can come up to me after and I can sort of point you to resources. So JSON, for those of you who don't know, is sort of how a data object that could be read by JavaScript. I think JSON stands for JavaScript Object Notation. And here is the line where we are transforming our image. It looks kind of easy. It looks too good to be true. And if we look at the source code, we'll see that what the library is doing is that it is passing our data through our convolutional neural network. You'll see that the image data is being cleaned up in the first 2 lines. And then that is passed in the first convolutional layer. Then that result is being passed to the second, and that result is being passed to the third, and so on and so forth. And as the image data is going through each layer, it is going through a mathematical transformation, kind of. Noise is dropped from the calculation. Certain features of our image are weighed more heavily, certain features are not. And that is not too dissimilar from what is happening here. So this is a painting I was working on for a few months in a class, and I worked on this painting over the course of several classes, so over the several hours, and I was working from a live model, and this live model would hold the same pose. So it goes from left to right, bottom, and you'll see that colors are dropped, the shadows are deepened, highlights are made lighter, different colors appear, disappear, and there are corrections to anatomy. So here is our result. For our purposes, I wasn't quite happy with this result, so for our purposes, let's just look at the output from our Python code. So here's a transformed image using the Python implementation of style transfer. So, did our machine create something new? Well, I wouldn't think to make a white dog yellow, for one thing. Another thing you'll notice is that certain patches of fur are made more prominent. Did our neural network just reproduce its training data? Well, this is a little harder to say. At first, we would say no, because it does not look that similar to the Van Gogh painting. But you'll also notice that the transformed image is mostly yellow. And it seemed like that our neural network was really fixated on the yellow of the hat and ignored most of the other colors in the Van Gogh self-portrait. And I suspect that the neural network kind of figured incorrectly that the hat in the self-portrait is the most important part of that image. Whereas it did figure out correctly that Ice the dog was the most important feature of that photograph. And so it thought, hey, since the hat and dog are important, and since the hat is yellow, the dog must also be yellow. Another thing you'll notice is that the photograph suddenly gained a border. And I think it's because the neural network kind of picked up on the black on the edges of the self-portrait. Now, the black is not part of the painting. It is a mistake. So I think this self-portrait was scanned, and the canvas of that painting did not reach all the edges, and so the black of the scanning bed showed up in the picture of the self-portrait. But maybe when it comes to art, inaccuracy is okay, because what would it mean for the artwork if the neural network was accurate? Now, style transfer is a computationally impressive task, but does the resulting image really say anything about the subjects or the artists? Does the resulting third image express anything? So here we have a couple photographs of Michelangelo's David. And one of the things that people kind of point out is that the head and the hands are larger than they should be. They're out of proportion with the rest of his body. Now, I don't know how true this is, but there is kind of an urban legend that Michelangelo did this on purpose. He knew that David would be placed on a podium several meters high, and that people would be looking up at the sculpture. And so he made the hands larger and the face and the head larger to draw attention to those features. Here we have Botticelli's Birth of Venus. So I used to work at an art museum, and one day my boss told us about a paper where they kind of studied how long a person would stand in front of the artwork, and the average time a person would spend looking at a piece of art would be 6 seconds. So people might not notice this right away, but the feet are totally anatomically incorrect in this painting. They do not look like real feet. And Botticelli knew this. So what he did was he kind of composed the painting in a way to draw attention away from the feet and towards Venus's face. Now, even though these works have inaccuracies and aren't anatomically correct, these inaccuracies of these works of art do not really take away from their expressive power, do not take away from their power to kind of describe the mythology happening in the paintings and in the sculpture. And art is really less about photorealistic, about photorealism. It's less about correct representation and more about expression. How does life, how does the physical world, how does this idea look to me, the artist? And even when people commissioned artists to do their portrait, it wasn't because there was a lack of photographic technology. It was because they intended the artist to sort of immortalize their likeness, to kind of create this object that would say more about the person, that would express certain ideas that a photograph or a photorealistic painting won't be able to do. I mean, just think about the presidential portraits that were recently commissioned by the Obamas. Of course, there are plenty of photographs of the Obamas out there. But they still commissioned contemporary artists to do their portrait in a way to capture their essence, to sort of tell their story that photographs couldn't tell. So here we have a photograph of cypress trees and a painting of cypress trees. Just to note, this painting is not of this exact scene. So you might recognize this painting as being by Van Gogh, and you'll notice that there are swirls, that the moon is yellow. And of course, in the real world, there are no swirly leaves. The moon isn't yellow during the day, it's more of a white. But that isn't really important. What we have here is just how this scene made Van Gogh feel. And in this painting, he's trying to express his viewpoint. He's trying to express a feeling that this scene evokes in him. So here we have a Cubist portrait painted by Picasso. And of course, this isn't how the person actually looked. And we might not actually know how this person really looked, but we do have a sense of who this person might be, to Picasso at least. So even though the dog is barely visible and there's too much yellow and the eyes have lost their subtlety and there's no contrast between foreground and background, and we could fix all this. We could tweak our layer so the yellow becomes less important to the neural network. We could tweak our math so there's better contrast between the foreground and background. So we could sort of tweak our error functions so certain features are weighed more heavily. Or we could do more epochs of training so the neural network's understanding of Van Gogh is better. But what would be the point of doing all that? I mean, even with the help of machines, and we can essentially create new Botticelli paintings, all we really have proved is something about machine learning. But did we make art? So in his essay, Art in the Age of Mechanical Reproduction, written by Walter Benjamin, who is this critical theorist or cultural philosopher, depending on who you ask. So in this essay, he says that art that is reproduced by machines loses its aura. But maybe art made with machine learning has its own special aura. And that in chasing accuracy and copying Van Gogh, we might be missing opportunities to discover what machine learning's aura might be. So as you kind of start off, as you like experiment with machine learning to create new images, to create art, I would invite you to examine the oddities, the glitches, and see where that takes you in terms of the artwork you're making. It's not a bug, it's a feature. Thanks for having me here. That's it.